on the board here, I have an object on the XY plane, and we'll pretend this is a golf ball. It's given an initial velocity, v naught, that is directed up and to the right, indicated by this red arrow. And the black line is just the path, the curve, that the golf ball follows. And you'll notice that the initial velocity is tangent to the path at the initial point, and this velocity has some angle, makes some angle with the horizontal axis, the x-axis. And so we'll call this alpha naught, or alpha sub-zero. That's the initial angle that this object is given. And you'll notice that it has an initial v naught x, an initial x direction, an initial velocity in the x direction, and it's got an initial velocity in the y direction, or v naught y. And at its peak, it'll be flying completely horizontally, indicated by this red arrow. And then at the ground, it will have some velocity pointed downwards, and have an x component and a y component. And you'll notice that as it's going down, it'll also have an alpha, or an angle that it makes with the horizontal, but this time it'll be negative, since the object is actually falling downward. The velocity vector is pointing down and to the right instead of up and to the right, as it does at the beginning here. Now, we call this distance right here the range. And the range is just how far the object has traveled before it hits the ground again, or before it reaches its original height that it started from. Notice that this black path, I kept drawing it past the point where it appears to hit the ground, because some of these problems are going to have projectiles that start off being hit from a cliff, so it doesn't actually hit the ground, or doesn't stop its motion at the exact same height that it started. And so that's why I've drawn it like this. But the range is how far it has gone before it comes back to its original height. And this distance right here is the maximum height. Just from here to the ground. So this will be the maximum height of the projectile. And at every single point along this curve, the object is going to be experiencing the force of gravity. So throughout the whole motion, pulling down on it is going to be the acceleration due to gravity, or a sub y. And so what we want to do now is start looking at each point and start defining what v naught x is and what v naught y is, and using these to plug into those two equations that we saw. Okay, so let's start off by looking at the motion in the x direction. And we'll start off by looking at the acceleration in the a direction, or in the x direction, which is just a sub x. And it turns out that in these projectile motion problems, a sub x is just equal to 0. So the object, as it moves from left to right, is not going to be accelerating. The velocity in the x direction will be constant, and it won't be changing. So what that means is that the initial velocity in the x direction, which is v naught x, is going to be equal to the velocity in the x direction at any point along this path. So the velocity in the x direction here will equal to v naught x. It'll equal to the velocity in the x direction here will equal to v naught x. And even here at when the object hits the ground, the v naught x here, or I'm sorry, the vx here is going to be equal to the v naught x here. So this leads to the fact that v naught x is just going to be equal to the velocity in the x direction at any point on this curve. And so it turns out that now, since this is true, we want to find what v naught x is. So that's the next variable that we'll look at, is the initial velocity in the x direction. So we have our initial velocity vector, and I can draw it like the side of a right triangle, the hypotenuse side of the right triangle. And so this side length would represent the initial velocity, v naught. It's the magnitude of our initial velocity vector. And this side would be the initial velocity in the x direction. And this angle that it makes would be the initial angle, alpha naught. And so if you remember that the cosine of this angle, alpha naught, is just equal to the adjacent side, which is v naught x, divided by the hypotenuse, which is v naught here. And if we solve for v naught x here, we get that v naught x is equal to v naught times the cosine of alpha naught. So that's an important relationship. Both of these, the fact that ax is 0 and v naught x is equal to v naught cosine alpha. So we're going to use these later on.